Freely falling bodies. Freely falling bodies have free fall motion. So let me define what free fall motion is for you. Objects in free fall are in the absence of air, they're near Earth's surface, and they experience the same acceleration of negative 9.8 meters per second, also can be said as negative 9.8 meters per second squared. The implication here is that if two objects are dropped from the same height at the same time, they will hit the ground at the same time, regardless of their mass. Objects can be in free fall even if they're moving upward, as long as the three conditions of free fall are met of no atmosphere, the object is near the Earth's surface, and the only force acting on the object is the force of gravity, and therefore there is an acceleration that is constant, and that is a value of negative 9.8 meters per second squared. This acceleration value has a special symbol g, and it is called the acceleration due to gravity, or the gravitational field. Okay, so now I'd like to talk with you about Galileo's law of falling bodies. And this has a lot to do with that objects all fall at the same rate regardless of their mass if they're near Earth's surface and they're in the absence of air. And Galileo Galilei was able to figure this out through a very famous experiment, and I want to talk with you about that experiment right now. So, some sort of object is dropped from rest vertically, although Galileo more likely took spheres and rolled them down inclined planes. We're going to look at these objects falling vertically. So we have an object, it's going to be dropped from rest. And what Galileo noticed is that for every unit of time that the object fell, it would increase its distance by an odd number. So for example, in the first unit of time, the object would fall 1 unit of distance in the first unit of time. So in red, we'll use for distance, and let's use the color black for time. So after the first unit of time, the object would then fall 3 units of distance, represented right here. And in red, we'll show you 3. So for the object to travel the first unit of distance and then the next 3 units of distance, that takes 2 units of time. For the third unit of time, the object then fell 5 units of distance, and that is for a total of 3 units of time. What Galileo realized is that when we look at the first unit of time, we have a total of 1 unit of distance, but if we look at the next value, the 2 units of time, we have a total distance fallen of 4, and we look at the total of 3 units of time, we have a total distance fallen of, 1 plus 3 plus 5 of 9. And what Galileo realized is that 1, 4, and 9, those are the perfect squares of 1, 2, and 3. And so with this, Galileo saw a relationship between the distance an object fell and the unit of time. And so Galileo wrote this expression here to say the distance an object falls is directly proportional to the square of the time at which it falls. And once Galileo had this piece of information, he was able to derive an equation. And so this is one of the first equations, the first kinematics equations derived, and this was done by Galileo before calculus was invented by Isaac Newton. So how did Galileo derive this formula? So let's write again his relationship that the distance an object falls is directly proportional to the square of the time. Now, what in the world does that mean? Well, this alpha symbol, this Greek letter alpha, basically what that means in mathematics is that alpha, that directly proportional to, is an equal sign and next to that you insert a constant. Sometimes it's just written as a c for constant, and then everything else is the same. So you have your t squared there, and you have your d there. The question here is, what is the constant? And so it turns out if you can show a linear relationship between your distance and your time, you could find the slope of that, and that is your constant. So let me show you what I mean. I want to do a graph of my expression. On my vertical axis, I will have the distance the object falls. On my horizontal axis, if I put just time, I will get a graph from the data that is parabolic. But I don't want a parabolic graph, I want a linear graph. So what I'm going to do is square the time here, and what ends up happening is when you plot your data, you can get a best fit line. And it's from this best fit line we could then find the slope of. And so the slope of this line will be, if we look at that, it's just the change in your rise divided by the change in your run, or delta d divided by delta t squared. And so my slope is equal to the delta d over delta t squared. That is also equal to the constant in the above expression. And when Galileo did his experiments, it turned out the constant value ended up being 1/2 of the value of g, or 1/2 of the acceleration due to gravity, or 1/2 of what we call the gravitational field. And that ends up being, the magnitude of that ends up being 4.9, and the unit, of course, is meters per second squared. It's pretty exciting. So I want to go ahead and show you the 3 kinematics equations for free fall that you're going to be responsible for. The first one being the formula that Galileo derived through his experiments and his graphs. So let me go ahead and write those down for you. So here are the kinematics equations for free fall. Please note that equation A is the equation that Galileo derived. It's just the one that Galileo derived is missing this term here. And the reason for that is this term includes an initial velocity, and when Galileo did his experiments, his objects all started from rest, so their initial velocity was 0. Also, I hope you can see here when you look at these equations, they should look familiar. They are the same equations we already talked about, but instead of looking at things in the horizontal direction, we are now looking at them in the vertical direction, or in the y direction. So you'll notice that the velocities here have subscripts of y, the displacements are noted with the letter y, and my acceleration has changed to the acceleration due to gravity, or the g, because these objects are in free fall, and that is the only constant acceleration that they will be experiencing. Okay, it's time for an example. So we have some sort of cliff or edge here. It's 50 meters high. Someone is standing on the top and they throw some sort of ball upward, and then it comes down past the edge of the cliff all the way down to the ground. I'm actually going to make the top of the cliff my initial position. My y-sub-naught, I'm going to call that 0 meters. There's going to be an initial velocity for when the person throws this at the top of the cliff. And there is going to be an acceleration in the y direction. We're going to call that g. And if we assign upward as positive, plus y, then my acceleration due to gravity is going to be a negative 9.8 meters per second squared. So this is drawing my picture, and this is all my givens so far. One last thing, I believe there's a numerical value for that initial velocity going upward from the top of the cliff there, and that's going to be 20.0 meters per second. Okay, so the first thing for part A we're going to find is, what is the time does it take for this object to reach the maximum height in its flight. And one of the things I know is that the very, very top of its flight here, the velocity is going to be 0 because the object actually needs to stop so it can change direction. So my velocity at the very top, sorry, v of the top, is going to be 0 meters per second. So the question is, what formula am I going to use based on my given and what I want to find? The formula that I would like to use is one of the kinematics equations, v sub y is equal to v sub naught y plus g delta t. I just need to rearrange this equation for delta t, and I get delta t is equal to this expression here. So now what we're going to do is solve, and we're going to plug in numbers for our variables. Plugging in our numbers here, and then I get my answer for delta t of 2.04 seconds. And my answer comes out to be positive. That's a very, very good thing when we're solving for time. We want it to definitely be positive. Now part B wants to know, how high up does this object go? What is what I want to call y sub max, question mark. If I draw that in the picture here, that's going to be, I'll have a y here, and it's going to be the height above what I call 0. And somewhere, let me see if I can fit in max in here. We'll just squeeze that in there. Okay, y sub max. So what is that? The formula I'm going to use, based on the information that I have, is the one from Galileo's Law of Falling Bodies. That formula, which is the y max is equal to y sub naught plus v sub naught y delta t plus 1/2 g delta t squared. We have all the information. The only thing we didn't have to solve this problem earlier was time, but we found that in part A. So now all we need to do is plug in the numbers. So let's go ahead and do that. So plugging in the numbers, I get my value for y max of a positive 20.4 meters, or 20.4 meters above the cliff. Part C says, as the object goes up and back down, what is the speed of, rather, what is the velocity of the object the moment as it's coming down, but it's at the same height from when it initially came up? So if this here is v sub naught, what is this here v? So we want to go ahead and prove, what is that? The formula we're going to use is this one here, and I wanted to point out to you that this delta y value is the one of interest. This is your change in position, your change in your vertical position. And if you look at this diagram here, you'll see that there is no change in vertical position. There is no displacement in this case. So this delta y becomes 0, and therefore this whole term becomes 0. And in essence, what I have shown here is that my v sub y is equal to plus or minus the square root of my v sub naught y squared. In other words, my v sub y is equal to a negative v sub naught y. So they're equal in magnitude, just opposite in direction. And lastly, if I have a delta t of 5 seconds, what is my Vy, and then what is my y in relationship to the top of the cliff? Let's review the givens. We already have the acceleration, which is g. We also have our initial vertical velocity of a positive 20.0 meters per second. Okay. For my Vy, I'm going to use this kinematics equation. And plugging in our numbers. Get my answer of negative 22.5 meters per second. Well, what about my position? How has that changed? Well, the formula I'm going to use for that one is, of course, Galileo's formula. My y is equal to y sub naught plus b sub naught y delta t plus 1/2 g delta t squared. Plugging in my numbers. I get an answer of negative 22.5 meters. That negative means that the object is 22.5 meters below the cliff. Thanks for watching.